Alright, welcome back everybody. So today we'll be looking at the Leetcode problem, k closest points to origin. Now this is actually a very common problem, and I was actually personally asked this when I was interviewing at Amazon. So they like to use this question a lot. Actually, a lot of big companies do. I think it's more prevalent at Amazon, but regardless, it is a very common problem to be asked. And the reason being is because one optimal solution uses a data structure that not a lot of people think to use, but it's also a very important one to understand. So with that being said, let's just read the description. We have a list of points on the plane. Find the k closest points to the origin 0, 0. Here the distance between the 2 points on a plane is the Euclidean distance. You may return the answer in any order. The answer is guaranteed to be unique, except for the order that it is in. And so as we can see in the examples, if you don't know what a Euclidean distance is, essentially it's taking the coordinates x and y and square rooting both of them and then adding them together. So as you can see right here for input coordinates 1 and 3 and then negative 2 and 2, and we have k of 1. So that means we have to return one closest coordinate to 0, 0. So in this case it's negative 2, 2. And the reason being is because if we square root 1 and 3, we get 10. And if we square root negative 2 and 2, we get 8. And so 8 is obviously closer to 0, 0 than 10 is. So the answer is negative 2, 2. And then similarly, with the example 2, we have coordinates 3, 3, coordinate 5, negative 1, and then coordinate negative 2, 4. We want to get the two coordinates that are closest to 0, 0. So inevitably, after performing the Euclidean distance formula, we get an output of 3, 3, and negative 2 and 4. And it also says that the output can be returned in any order. That doesn't have to be specified, so negative 2 and 4 and 3, 3 would also be valid. So hopefully that makes sense. If you don't fully understand what Euclidean distance is, we'll have the formula written out in the conceptual overview, so don't worry. But with that being said, let's just jump into it. Okay, so let's first start things off by just having some coordinates. So let's just start with the very first one. So we have 1 and 3, negative 2, 2. And then k is equal to 1. And so what's the simplest way that you can think of solving this? The first thing that comes to my mind is if we're dealing with a list and if we're dealing with a k amount, so we want to get k closest to origin. So that tells me we want to get the k smallest items. And so the simplest way to do that is if we perform, the calculations for each item in the list as we go through the entire list. So, and then after we perform the calculations, we sort the values and then get upwards of k, so we can just get upwards of k values, and this will be our answer right here. So remember, these colons essentially are slicing. So when we say colon k, we're essentially saying from the beginning of the list upwards of k. So in this case, k is 1, so that means we'll only get the value up to here. So if we perform our Euclidean distance formula, remember so we multiply x by x and y by y. So we get 1, 1 plus 3, 3, right? And so at the end of the day, this is equal to 10. And then here we get negative 2 times negative 2 plus 2 times 2. So this will be 4 plus 4, so we get 8. And now since we've sorted it, 8 will be the first in the list. So if we say upwards of k, we'll get the first value here, which you can imagine is just being 8, and that will be our answer. Now that is the quickest way to deal with this, because if you sort something and then just pull upwards of k values from it, then, there you go, that's your answer. It's pretty straightforward. It works, but it's not the most optimal solution because most sorting functions and most programming languages run in O of n log n. And it's not the greatest runtime because we can definitely do better than this by leveraging a different data structure. And so sorting works good for a brute force, but because this is our biggest bottleneck, we need to improve upon that. How do we improve upon n log n? Well, in our case, since we're only keeping track of k values, that's all we're interested in. So what can we do? One thing that we can use is a data structure called a heap. And so a heap, there's two distinctions. You can either have a min heap or a max heap, but they both perform the same thing. So if in a min heap, the heap keeps track of the top minimum values. So you can imagine, let's say we have a min heap of 5 values. So it looks similar to a tree. So let's say we have 1, 2, 3, 4, 5. So a heap looks visually similar to a tree, and all it does is it stores values in either ascending or descending order depending on if you're using a min or max heap. And so in this case, this would be a min heap, right? So min heap. So we'll store the smallest value first. So we have 1. And then let's say we get rid of 1, then our min heap will look something like this, right? So we get rid of 1. The min heap itself will rearrange to keep track of the smallest numbers in ascending order. And so now it'll look something like this. 1 is gone and it's rearranged itself with 2 being the smallest number. So min and max heaps just keep track of the smallest or greatest items in an ascending order. With the root, so the root will always be either the smallest or greatest item depending on if you're using a min or max heap respectively. You may be thinking, how does that fit in here? Well, again, because we're only interested in k values, what does that tell us? If we can have a heap that keeps track, or that is the size of k, then when we're done iterating through our lists, all we have to do is just convert all the values within our heap into a list, and then that's our answer pretty much, right? So if we look at this simple example right here, remember as we go through, we calculate the Euclidean distances. So we're going to be dealing with 10 and 8. And so every time we calculate a distance, we add it to our heap. But if it's equal to size k, so in this case, if k is equal to 1, or if our heap is equal to 1, then at which point we'll start removing items until it's equal to k. If it's equal to k, then we'll start removing items, otherwise we just add to it. So looking at our input that we calculate, our Euclidean distance, we'll have 10. So for this specific approach, since I'm doing everything in Python there's no max heap, which is another way to implement this, but in this case, the heap in Python is always a min heap. And so we kind of need to work around the constraints of the problem. And so let's add the calculated distances to our heap. So when we first start out, we'll have 10, but then it'll be equal to size k. So then we can remove this, and then we come to 8. And then we can return the associated value with this distance, which would just be -2. This is a really simple example, but real quick, let's just look at an example where we have a larger input. So just to save on writing, I won't write out a list of coordinates. What I will do is just write out their Euclidean distances. So let's say, for example, we're dealing with 10, 8, 2, and k is equal to 2, right? So in this case, we want to get the 2 closest elements to 0, 0. So just looking at the answer, obviously 2 and 8 is what we're looking for, but let's just walk through it. So we have our min heap, right? So our min heap we'll start off the value of 10, and then when we come to 8, what will happen is it'll readjust. So we'll get rid of this, and it'll create another node, and so 8 will be the smallest, and then we'll have 10. Now at this point, our heap is equal to size k. And so when we encounter 2, we have to pop first, right? And so when we pop from the heap, what we'll do is remove 8. And so now our heap looks like this. And then we can add 2, which will then look like this. So as you can see, this is not correct, right? Because we're looking for, remember, 8 and 2. In Python, since all we can work with is a min heap, we need to account for this small edge case. So this may not be present in other languages, but for Python specifically, since that's how we're writing all of our problems, it bears talking about. The min heap keeps the smallest item at its root, right? And so in this case, we don't want to get rid of 8. We want 8 to be in the answer because we know just by looking at this 2 and 8 is are the closest items to 0, 0, right? And so how do we do this? All we can simply do is when we calculate our Euclidean distance, we set everything to negative, right? So let me just walk through how that would work. So going through this example again, we have -10, and then we encounter -8. And so when we add -8 to our min heap, -8 is greater than -10. So what will happen is -10, and then we'll have -8. So this is what we're looking for. The smallest item is at the root, right? So smallest element. So element. Smallest element is at the root. -10 is the smallest. And so when we reach our size of k, now when we remove, it'll look like this. And so now -8 is our smallest element. And since we've run out of elements to put in our heap, this is what the heap looks like. This is the end state right here. And so when we pop these off, then we know we'll have the right answer because -2 and -8 is what we're looking for. And so we can essentially add the proper coordinates associated with these Euclidean distances as our final output. And so that is just an important edge case when dealing with Python because we don't have a max heap. So we have to just essentially inverse the value of every number to negative just so we can sort of work around this little limitation with our min heap. It's important to fully understand how a min heap and max heap works. So I encourage you to make sure you study that and understand it on your own time because these distinctions will really help you understand when to use which for a particular problem. So if you're trying to keep track of small numbers, then maybe go for a min heap. If you're trying to keep track of larger numbers, then go for a max heap, but just fully understand it and know which one to use for the situation. And so that's pretty much all there is to this problem. So now is a time when we talk about runtime and spacetime complexity. So let me find some space over here. And so with our heap, our runtime will be O of n times log k. And the reason being is because n is our input. So in the problem it's called points, but it essentially just holds a list of coordinates. So that's n times log k. And so log k is specific to the heap because when you insert an item into a heap, like right here, since we're inserting as we find new values, whenever you insert into the heap, that's a log k operation, where k represents the size of our heap. And so our space complexity is just O of k. And so O of k just means that our heap holds up to k values in the worst case scenario. And so yep, that's pretty much it. More efficient than our first approach, and it uses a powerful data structure as a heap. I highly encourage you to keep looking into the heaps because, like I said, they're a powerful data structure and they can be used in a lot of different scenarios. And not a lot of people think to use it, but sometimes it could be the answer to your problem. From my personal experience, I've encountered interview questions where I've exhausted all data structures I would normally use, but then on the offhand, I thought about a heap and I applied it to the problem and it solved it. So just remember, this is kind of an out there data structure, but you never know when you might need it, and it only benefits you to learn from it. So hopefully you learned something with this, and now we're going to go jump into the code. Okay, so now we're going to write the code for k closest points to origin. And so remember, this approach mainly utilizes a heap. With Python, we can just actually import one, so import heap q. So that's pretty much how we access our heap. And so we also need, we're going to utilize an auxiliary list, which we'll call heap. And what this will do is it's the value that we pass to our heap functions so we can sort our data. So this is a necessity. If you don't understand it, I encourage you to look at Python heaps and try to understand how the functions work and how we need to set things up. We're going to have an empty list called heap, and then we're going to iterate through our points. Now, our points, remember, are essentially lists with two values, x and y coordinates. So what we can do is we can actually iterate like this, x and y. So we can iterate by looking at 2 points at a time, or the two coordinates at the same time. So n points. Hopefully that makes sense because remember, this is a list of lists, so we can access x, y. At which point, what we'll do is we will calculate our distance, right, or Euclidean distance. And remember earlier, I said with Python, we need to inverse the numbers because of our min heap. So what we'll do is we'll say negative and then x times x plus y times y. Remember, just the example I talked about before we came over to the code walkthrough is, if we have 10, 8, and 2, if we want to get the two smallest numbers, the smallest number, -10, will be at the top of our min heap. And so when we pop that off, when we reach size of k, we'll have the proper numbers that we want in our final output. And so that's why we convert to negative. And then all we do is we check if the length of our heap is equal to k. Just hold our values, and then we call heap functions to sort our data accordingly. And so if we reach the size of k, we're popping data off. We're just popping off the top of the heap so we can maintain the size. And so that means we call heap q, the function that we imported, and we'll say heap push pop. So this is just essentially popping, and we need to pass it two parameters. So we pass it our heap, and then we pass it a tuple, and the tuple is what we'll be sorting by. So we'll say we'll sort by the distance and then x and y. And so this will be for our reference later so we can pull this data and construct our final output. And then we'll say else. So if it's not of size k, just keep adding to it. We'll take this. The code is very similar. Instead of heap push pop, it's just heap push. And then we pass our heap and then dis and x, y. So that's pretty much the core logic. I mean, the heap pretty much abstracts a lot of the logic that you would write if you didn't use it. So it's a very powerful data structure and it suits us perfectly for the needs of this problem. And then finally, we'll just return. We're returning a list of lists. And so one way we can do this is we just say get x and y from, because remember, we add this to our heap. So essentially we have a tuple with 3 values, but we're only concerned with x and y because those are the coordinates. So we can just say get x and y for this x, y. So we're just pulling x and y from these 3 values. And where are we getting them from? We're getting them from our heap. And so this is just shorthand syntax in Python. So no need to worry about it there, but I mean, you could easily do this in a for loop too if you wanted to. But yeah, I believe this concept is called list comprehension, if I'm not mistaken, in Python. So you can look into that. This is pretty much it. I think if we run this, we will get our proper answer. So let's just hit that. Oh, right. So K, my mistake, should be capitalized. So let's run this. Okay, so we got the proper output for the first example. Now let's submit this and see what we get. Awesome, and it runs pretty efficiently because of our heap. That's pretty much it. Hope you guys learned a lot. Remember to dive deep into the heap data structure, and it works very well in a specific situation, so you should definitely know it for the coding interview.